Hey everybody, this is a lecture on momentum, including some practice problems and a few different ways of thinking about momentum. So I'll start with a question. A golf cart and a pickup truck are approaching you, both at 10 miles an hour. You don't have time to dodge both. Maybe you're stuck inside of a narrow tunnel and there's nowhere to go. Which do you choose to get hit by? Well, if I had to choose, I would definitely choose the golf cart over the pickup truck, because even though they're coming at me with the same speed, the pickup truck has a ton more mass. And momentum, well, and because it has more mass, it has more momentum. It's going to basically knock us a lot harder than a small golf cart going at the same speed. So momentum kind of tells us about the amount of oomph that something has. The definition of momentum is just mass times velocity. So it's sometimes thought of as mass in motion. Something that isn't moving has no momentum. It has no oomph because it's not moving. Something with more mass or more velocity has more momentum. This is a simple definition. Momentum, P, is equal to mass times velocity. Part. So momentum is mass times velocity. That's our equation, and it is a vector. So unlike energy, momentum has a direction, which means a change in the direction of motion is a change in momentum. The SI units for momentum are going to be the units for mass times the units for velocity, kilograms, meters per second. We could also use newtons times seconds. Those are equivalent units. It doesn't have any special names for its unit. Doesn't have any special names for its unit. So this is just an illustration of a baseball bat hitting a baseball. And momentum is actually going to allow us to analyze situations in which there's large forces applied for short amounts of time, like when there's an impact. The law of conservation of linear momentum is one of the most fundamental laws of nature. It's always true. The law states that in a closed system, which is not acted upon by outside forces, total momentum is conserved. And that's the vector momentum, not just the magnitude of all the momentums. Well, that means also that in our universe, the total momentum is always conserved because there are no forces coming from outside of our universe. The nice thing about momentum, unlike energy, is momentum cannot change form, which means it's much easier to keep track of than energy. We can just look at the mass times velocities of all the objects and see that the total momentum has to stay constant. These diagrams show us some collisions between galaxies or interactions between galaxies. And anytime there's an interaction between galaxies, the total momentum stays constant. So if one pulls on one, the other pulls on the other by the same amount. And they change velocity or they change momentum by opposite amounts. So let's do an example. Which experiences the greater change in momentum? Two 0.20 kilogram rubber balls are hit directly towards different walls. Should be different walls. Each impacts with the same initial speed of 20 meters per second. Ball A hits a stone wall and rebounds directly back at a speed of 18 meters per second. Ball B hits a bulletin board and rebounds directly back at a speed of 10 meters per second. We want to find which experiences the greater change in momentum. So if you think about this for a second, they both start out at the same speeds. So this is going to be A. So they hit the wall at 20 meters per second. I'm going to do two walls, one wall over here and one wall over here, B. 20 meters per second. And they bounce off with a new velocity. This one, 18 meters per second. And this one is going to be 10 meters per second. So you might say that the one with the greater change in momentum is B, because it starts out going at 20, it ends up at 10. That's a difference of 10. But we're not thinking in terms of those speeds as a vector. Let's actually calculate our changes in momentum. So if we think about change in momentum is going to be change in mass times velocity. where velocity is a vector. But in all of these cases, our masses are going to be the same, so we can just factor out that mass. It's going to be mass times change in velocity. So we can just plug in our numbers, mass times final minus initial velocity. But remember, velocity is a vector also, as momentum is a vector. So let's find the change in momentum of A. Well, it has a mass of 0.20 kilograms. The final velocity is negative 18 meters per second. That negative sign is important because it's moving to the left, minus our initial velocity, 20 meters per second. So we get 0.2 times negative 18 minus 20. Notice our change in velocity here, negative 18 minus 20, is actually negative 38. And we get a change in momentum of negative 7.6 kilograms meters per second. So that's one way to calculate our change in momentum. I'm going to do it a slightly different way in B. Change in momentum is just going to be equal to momentum final minus momentum initial. So I'm going to calculate my final momentum. It's just going to be mv final minus mv initial. So 0.2 times 20 minus 0.2 times, and it's negative 10 meters per second. I'm omitting the units. 0.2 times 20 is 4 kilograms meters per second. That's our final momentum. Minus 0.2 times negative 10 is negative 2.0 kilograms meters per second. So when we do 4 minus negative 2, we get 6.0 kilograms meters per second. So we can see, did I do that right? I switched my final and initial velocity here, actually. So really it should be, we should switch these and we'll end up with a negative 6 here. That's my mistake. Negative, so that's going to be a positive. And we still end up with the same magnitude answer, but it's negative 6. Anyway, it's clear that A experiences the greater change in momentum, even though it ends up with a speed that's closer. It's because momentum is a vector. So we can also relate momentum to kinetic energy. They're both written in terms of masses and velocities, so let's come up with an equation to relate them. We know kinetic energy is 1/2 mv squared and momentum is mv. So if I want to write momentum as something closer to kinetic energy, I see that there's a v squared, so I'm just going to square both sides of this. And I'm going to get p squared equals m squared v squared. Well, I'm going to make the right side into kinetic energy. So I'm going to multiply both sides by 1/2. I get p squared over 2 equals m squared v squared over 2. Now, if I want this to be 1/2 mv squared on the right side, I need to divide both sides by m. So I get p squared over 2m equals, well, m over m, or m squared over m is just m. I get mv squared over 2. So our right side is kinetic energy, our left side is momentum, so we can write kinetic energy is p squared over 2m. Now that's just the magnitude of the momentum plugged in there. Energy is not a vector, but still it's a really useful relationship. If we know momentum and the mass, we can find the kinetic energy. Let's do an example. An alpha particle is a radioactive particle made of 2 protons and 2 neutrons. It has a mass of 6.64 times 10 to the minus 27 kilograms. When radioactively emitted from an unstable nucleus, it has a kinetic energy close to 5 MeV. That's 5 mega electron volts. Find the momentum of a radioactively emitted alpha particle, and we're given that 1 eV, that is 1 electron volt, is 1.60 times 10 to the minus 19 joules. So we're given our mass is 6.64 times 10 to the minus 27 kilograms. We're given our energy is 5 mega electron volts, but we need to convert that to joules in order to get sensible units, so let's convert. Well, 5 is just 5. Mega means 10 to the 6th, so 5 times 10 to the 6th. And then we're left with just electron volts. 1 electron volt is 1.60 times 10 to the minus 19 joules. If we multiply that out, our energy, that is our kinetic energy, kinetic energy equals 1.6 times 10 to the minus 19 times 10 to the 6 times 5. We get about 8.0 times 10 to the minus 13 joules of kinetic energy. Now let's use our equation and find the momentum. We know that Ek equals p squared over 2m. So if I multiply both sides by 2m, I get 2m times our kinetic energy is p squared. If I square root both sides, I get p equals the square root of 2 times the mass times our kinetic energy. Plug in our numbers. 2 times 6.64 times 10 to the minus 27 times 8 times 10 to the minus 13. I'm going to do the units at the end because they're all in base SI. I get my momentum equal to 1.0 times 10 to the minus 19. And the units are going to be kilograms meters per second. It's a tiny particle. It has a very small momentum. It also has a very small mass and a very small energy. So we can also talk about Newton's second law of motion. We usually think about it as F equals ma, or net force is ma, but that is not how Newton wrote his original second law. Newton thought of everything in terms of momentum. And so Newton's second law was written as net force is equal to change in momentum over change in time. Really, F equals delta P over delta T, which tells us that force is the rate of change of momentum. That is, the net force is the rate of change of momentum. And we can see how this is F equals ma if we expand it out. We can, actually, let's do it down here. Let's rewrite it down here as F equals change in mv over delta t. Well, because mv is momentum. Well, usually our mass is constant, so we can factor that out, and we get F equals m delta v over delta t. But delta v over delta t, our rate of change of velocity, is just acceleration, so that's ma. So it is equivalent to F equals ma. It's just a different way of thinking about it. So this tells us that if we have a momentum that changes over a very short period of time, it requires a great force. If our same momentum changes over a long period of time, it is a smaller force. When you hit a golf ball, that golf ball gains a lot of speed in a tiny, tiny, tiny amount of time, which means it takes a lot of force to change the momentum of that golf ball. So let's do an example. The graph shows the variation of momentum with time for an object. Find the force on the ball between 0 and 2 seconds, and the force between 2 and 4 seconds. So we're going to use what we know about Newton's second law. F equals delta P over delta T. So that's the rate of change of momentum. Since this is a momentum time graph, momentum is our vertical variable, time is horizontal. force is just going to be the slope, our delta momentum over delta time. So the force from 0 to 2 is just going to be rise over run. Change in momentum is 20 kilograms meters per second. And the time is 2.0 seconds. 20 over 2 gives us 10 meters. Oops, that's 10 kilograms meters per second squared, or 10 newtons. The force from 2 to 4, again, rate of change of momentum, but our momentum is not changing, it's constant. Our slope is 0. So that means when we plug into delta P over delta T, it's just going to be 0 over 2 seconds, which equals to 0 newtons. This should make sense. If our momentum isn't changing, our velocity is constant, which means there's no force acting on the object. It's in equilibrium. The net force is 0. So using this, we can see that force is the slope of a momentum time graph. Usually we don't use these graphs, but you might need to relate that to a graph, just like we did. So in summary, momentum is mass times velocity, and it is a vector. Force is the rate of change of momentum, delta P over delta T, that's Newton's second law of motion. And kinetic energy can be written in terms of momentum as P squared over 2m. Hope that was helpful. Bye.